You're now listening to the Deep Edge Podcast with your host, technology expert Ray Moda, giving you the rundown on telecom, cloud, and all things business and tech. This is the Deep Edge Podcast. Let's go!
Hi, Peter. Welcome to this edition of the Deep Edge Podcast. By the way, before we get started, Peter, how are things in California?
Well, Ray, it's a crazy time. Everything is locked down, shelter in place, and but I can tell you, I've been getting a lot of work done.
That's good.
Because there's nothing else to do. But the other thing, though, that I do feel good about is that San Francisco Bay Area is one of the first places to really do the shelter in place. And if you look at the numbers, the number of deaths and cases, it really shows in the numbers taking that action early. So I feel I didn't like it, but I feel good about it, and I feel like they made the right decision. I'm hoping that we can come out of this soon, get back to normal.
Yeah, I know, it's kind of odd. I feel like I'm living in one of those movies I used to watch all the time and stuff like that. So I agree with you. It has certain things where you're like, this thing needs to end, at some point there, because some people are driving each other crazy. Now, I live in Arizona where it's different aspects than California, so they kind of have like a quasi point of view. But one thing I noticed, Peter, is that people we're in this technology space and telecom for many years, right? Or I should say decades, right? I think the normal person is realizing that the importance of telecom, right? The importance of connectivity, because you see all this remote working, even now where we're talking. Normally, I would be in front of you with all this fancy equipment. Now we're doing it from our homes, right? And a lot of these businesses are embracing remote working and communication.
Yeah.
So I think there's going to be parts where governments are going to have to get involved to help, because it impacts the economy, the GDP, it impacts people's social life. That piece. So I do see that there's going to be some areas that are going to be what we call the new norm going forward. I think there's going to be some businesses out there that go, do I really need to spend $10 million for that building? I'm realizing my people are actually productive working from home. You've been working from home for a very long time. You agree with that, or?
Yeah. Oh, yeah. I've been working remotely for years and years, doing the work with ACG, but also I worked at Cisco for many years, and we pretty much worked as a virtual company at Cisco. I work with people all over the world, so I'm pretty used to it.
Yeah. Now, Peter, you're our CTO, right, for ACG, and you work part of the analytics group, and you do a lot of the business case. What I want to do as part of this podcast is honestly just have a discussion, right? And one of the key areas that you've been extremely busy working with a lot of the models is all related to this RAN space, right? And how does what are the changes in the RAN? So what I want to do is ask you, why is this becoming important all of a sudden, and why are the phones ringing off the hook regarding these debates on modeling and architecture? Maybe you could share some light with the expertise you build on that.
Sure, yeah. Well, so let's start out with, if we look at the RAN, which is the radio access network. Right, that's the biggest part of a mobile network in terms of just geographic size, as well as in terms of the cost. Right, because if you think about it, it's all the base stations, all the radios, all the backhaul required for those radios, and all the equipment required to do that, and then you're bringing it back into the core of the network, which are less devices, right? So the RAN is a big part. It's an expensive part, so it's always been something that's of interest.
Yeah, and I've seen that in some cases, Peter. I don't know if you're modeling. In some cases, I've seen where the RAN could be between 60 to 80% of the overall network cost. Is that what you're seeing in some areas?
Yes, definitely.
Yeah. Now, what are the decisions that are having to be made? Like, what are the present mode of operations, and why are people considering new architectures in that space?
Yeah, so one of the things that I've been working on, and the ACG in general we've been very involved with, is the whole area of Open RAN. Sometimes we call it VRAN, virtual RAN. We also call it CRAN, or Cloud RAN. Okay, so there's actually three acronyms, a little bit confusing. However, Open RAN is probably a good one.
It's a good one.
There's a whole standards body focused on the Open RAN. So, honestly, Ray, when I first got involved in this and started looking at a virtual RAN, I was just scratching my head. I was like, what do you mean a virtual? I mean, I understand you have virtual routers, virtual packet cores, all that stuff. But RAN seemed like it was fundamentally kind of hardware based, right? Anyway, so I, after getting involved with it, now I have a very good understanding of what all the Open RAN, the virtual RAN is about, and more importantly, we've been doing a lot of modeling and simulation work on the economics around that, because the key thing is, and especially as carriers are going to build out 5G networks, right? It's going to cost a lot of money.
Right. Okay.
There's a lot of capex. There's an enormous amount of opex, and it's not clear that at least the consumer revenue is going to be that much higher. For where's the money going to come from to pay this? Now, there's going to be a lot of revenues on the business side, but clearly optimizing the expenses of the biggest part of the network, which is the RAN, is extremely important.
Right.
So so I can spend some time.
Let's go over maybe, because in present mode primarily you see a lot of the DRAN offer. Maybe we can start off with the baseline on how it's addressed, and I think you created maybe one or two slides that we can go into it. And if possible, I'd like for you to show a little bit about some of the outputs that you're getting in some of this stuff here.
Yeah. So I've got a few slides here.
Yep.
So this is just kind of a brief overview. So this first slide shows what we call the DRAN, or the distributed RAN physical architecture. So this is typically the way RANs have been built, and almost all the RANs today look somewhat like this. So basically, we have a cell site. We have radios. You have 4G radios, 5G radios. Of course, there's also 3G and 2G. But in general, most of the focus right now is on the 4G and the 5G radios. Okay, now the radios then connect to what's called a BBU, or a baseband unit. So as you probably know, nowadays, there's very little analog left in the world. So most of the analog electronics is out here in the radio, but very quickly that analog gets converted into digital signals. Right? And then most of the heavy lifting in the radios is all done in digital, using digital signal processing and other approaches, and this stuff gets done in this what's called the BBU.
The BBU. Right.
Now the BBU then, and this is typically all in the cell site. So the radios will be up on the tower, and typically there'll be some fiber coming down. The BBUs will be down in a little building, or they could be outside as well. And then those BBUs will typically be connected to a cell site router. However, they could also, come back over dark fiber, or they could come back over WDM or other types of transport. But there's some way to and this is typically Ethernet coming out of the BBU and going back. Now, there's really, if you look at the costs of this, right, there's the cost of the radios, right? There's the cost of the hardware for the BBU, and these are, when we say physical BBUs, what we really mean is it's a specific appliance, built with ASICs, specifically designed to do these functions. And then there's BBU software. Okay, so basically the way the costs typically work, like I said, you pay for the radios, you pay for the BBU hardware, then you also pay for the BBU software, and that's typically based on how many carriers or how many different signals you're sending out on the cell site tower. Typically a tower will have like 3 different sectors. The sectors point in different directions, and then each sector can have one or two carriers or even more per sector.
Right. Now, when you say carriers, will you define what you mean by carriers there?
Yeah, so essentially a carrier essentially is the radio signal. So a simple way to look at it is, think of if you're listening to an FM radio and you tune into 91.9, and that's a specific frequency, it's a specific carrier that you're listening to, and then you switch to 89.9, and now that's a different carrier. So the same thing applies here to the cell site. So these different carriers, it's not so simple as FM frequencies, but they're essentially in different frequency domains that have been allocated, and for instance, you could have a 4G carrier and you could have a 5G carrier.
Right, okay.
Or you could have like multiple 5G carriers that are being used. Each carrier needs a radio, but then typically all those radios will aggregate in the BBU, and then there'll be software to deal with it. And typically the way the software is priced is based on the number of carriers. Right. But then in the typical architecture, we have something called backhaul, which goes from the cell site to a router, which will be in some kind of an edge or regional data center or central office. And then that's typically where the packet core is. And the packet core is probably a conversation for
another time,
different topic that we can discuss at some point. But this is where all the smarts is, essentially, in the packet core. So that's essentially what things look like today. So the key thing about this architecture is it's closed proprietary technology. So basically, there are really like three vendors out there today, three of the major vendors who sell this equipment, Ericsson, Huawei, Nokia, who pretty much dominate the market. And if a service provider chooses one or two of those vendors, they move forward and they deploy the proprietary solution. So the way I like to put it, it's kind of like the old days with the IBM mainframe.
Right.
You could choose IBM or IBM.
Right. Didn't have a choice. And it was SNA protocol.
Yeah. So it all had to work together. That's kind of the way the RAN works today. Of course, we know now in the network, everything has become very, very open, so we can mix and match routers and switches and all kinds of different things, and they all work together. Right. So let's look now at the ORAN or the Open RAN architecture, like I said, when I first started looking at this, I was thinking, how do you virtualize a RAN? That seemed to be a little bit complicated, but it's actually not so much. It is complicated, but it all makes a lot of sense. So let's just describe now a little bit about what the components are. Okay, so now the components of the RAN. Now we still have the radios. Okay, the difference in the Open RAN is that now the radios don't have to connect to the specific vendor's BBU. They're what we call open radios. So we really think of them as white box radios. They have a standard interface, which is called eCPRI. Okay, eCPRI interface is basically an Ethernet. The radios themselves will convert from analog to digital, but instead of sending out this digital what was CPRI stream. So in the present mode, in the current proprietary mode, there are these CPRI interfaces, but they're totally proprietary. You can't make one or the other. They're a pure digital stream. They're not packets. Right, okay, so eCPRI, the big difference there is that, number one, they're Ethernet packets. They're UDP Ethernet packets. So you can pass them through any router or any switch. And then they contain they contain the digital information coming out of the radios. Right. So why is that important? Okay, the reason it's important is now, since I have a standard interface, these radios become radios that can be manufactured by anybody. So I mean, some of the major manufacturers in China and other places that have the capability to build, large quantities of fairly complex hardware, they can do that and they can charge much lower prices because they don't need the same level of margin.
Right.
So I have this eCPRI interface. Now, the other thing is there are these different splits, and today I don't want to get into all the detail because that's a long.
Yeah, eCPRI could be a discussion in itself, right?
How that works, right? But what the industry around ORAN is focusing on the 7-2 split.
Mm-hmm.
So for now, let's leave the technical part out of that. But the basic idea there is it's how do I divide this stream from the physical level of data to the MAC level, and how do I do that division so that I can somewhat minimize the bandwidth requirements going back to what I call my DU pools, but also not put too much logic out here in the radios.
In the radio.
So anyway, I've got these open radios. Now, why are the open radios important? They're important, like I said, because essentially I can get better prices. They cost less. The radios are a huge part of the whole expense of these networks because you need a radio for every carrier. So now I have actually a couple of options here. So what's happened now is with the 5G standards, and it's also true with 4G as we go to Open RAN, I've split the BBU into two components. Okay, I've split it into a DU, so the DU is the distributed unit, and I've split it into a CU, which is the centralized unit.
Right.
So what used to be a single ASIC-based hardware component that we call the BBU now are these software components, which we call a DU and a CU, distributed unit, centralized unit.
Right.
And then, of course, we have the RU, which is the radio unit.
Right.
So now this DU and this CU can sit right at the cell site like they do now, or they can be distributed. Okay, so we have now multiple types of architecture. So it's actually quite a complex network now. So there is more complexity in the system, but as we're going to show, we get some very significant economic as well as technical benefits.
Right, Peter. Now, one thing here is I see that you have the radios connected in the cell site to a cell site router or MUX, right? The assumption is that if you're going with the MUX option, you probably need a bigger router by the DU side. Is that correct there?
Yeah. So basically, now one of the things, and probably the whole issue of backhaul, front haul, mid haul, we could have a whole nother topic on. But when we connect from the cell site to a DU pool, we call this front haul. So as opposed to backhaul, if we looked at the other diagram where we have the BBU and the cell site router, this is backhaul back to the packet core, right? So now here we have front haul, which is basically from the radios to the DU, and then there's another component over here which we call mid haul, which is from the DU to the CU, and then the backhaul is essentially from the CU to the packet core, which sometimes they'll be co-located, other times they'll be separate. So there's really three components: front haul, mid haul, and back haul. Now the key thing is the bandwidth requirements for front haul and the latency requirements for front haul are much more stringent than they are for backhaul.
Right.
And the reason is because you're basically sending a radio signal that needs to be processed by the signal processing components in the DU. So for that reason, if we're not going to locate the DU at the cell site, if we want to put the DU into a pool, those need to be at an edge site. Okay, so that's one thing. The other thing is that the DUs and the CUs, these are virtual.
Right.
So these are all software based, right? Because you think about it, right? When we said, okay, now we don't have that much analog anymore. So the analog is all out here in the radios. It becomes digital. It's sent over Ethernet. So instead of having to do that all in this ASIC-based device, now we can do that on regular old x86 servers,
right,
using virtualization.
Yeah, big cost difference there.
Yeah. So so again, what are some of the benefits here, right? Well, the benefits are when we open up the radios are less expensive, right? As we now go to a virtual model with x86 servers, we can end up with lower costs on the hardware side. Now, a server is actually more expensive than the ASIC-based BBU. However, when we create a pool of these servers, we can basically use the resources of single servers to handle multiple cell sites.
Right.
Also, when we create a pool, there's some other benefits that come in relative to signal processing and optimization, which can actually increase spectral efficiency.
Right.
Spectral efficiency is essentially the number of bits per hertz.
Yeah, that's a hot topic.
Essentially, it's very important, spectral efficiency, because spectrum is everything, right? Spectrum, yes. There's limited resource. It's very, very expensive.
Very expensive.
The more data we can push through the spectrum, the better. So spectral efficiency is kind of another benefit that we get here.
Right.
Now, so one of the issues here is that there's a lot of bandwidth required here. So now instead of having like in the old days it was gig backhaul, right, for everything, right? Now if we go to front haul, we really have to be at 100 gig if we're using a cell site router. Or, like I said, in some cases, we can even exceed 100 gig, depending on what kind of radios are being used. Like if we're using massive MIMO or something, right, that can actually, add up. So we might or might not use a router. There's also the ability to use essentially WDM. So it could be either CWDM or DWDM. Right. It could be passive or active. But in general, we're not going to be using like complex ROADMs because they're just too expensive, right? So the WDM technology has to be pretty inexpensive. The other alternative also is for service providers that have a lot of dark fiber. That's sort of the cheapest, easiest option is just bring it right back on the fiber. However, you can use up a lot of fiber doing that. Right. So anyway, the point is there's a bunch of options, but the key thing is that what we've done is we've centralized these DU servers in a pool. Now these are what we call far edge data centers. They'll typically be in like access central offices. They need to be really not more than 10 kilometers from the cell sites. Right. So we might pool like say 10 to 20 to 30, maybe even 40 cell sites connected to a DU pool, but they have to be within 10 kilometers of that pool. Right. And the DU is essentially the thing that's doing all the heavy lifting on the signal processing. That's why there's a lot of bandwidth required. Right. And then also that's why the latency requirements and the jitter requirements are really, really important. Because it's not just like straight old, packets. It's I mean, they are packets, right? But they can have a lot of latency. You can't have a lot.
Yeah, I've seen Peter. I mean, it depends on the size of the carrier too. Where there's a tier 2, where in some cases they might have a 25 gig type connection. But you're right. I mean, I think we're seeing some of those latencies in 4G be about 10 milliseconds, where now, depending on the spectrum that they buy, whether it's a high frequency or mid frequency, is a sub 1 second. But you're right, the spectrum parts associated with what the peak rates are, there's going to be a big difference going from 1 gig, I heard as high as to 30 gigs for 5G. So it's important to figure this out, because spectrum in a lot of cases is a large part of the acquisition cost to acquire that spectrum. So as you said, it's a vital part of it there. Yeah.
Right, and also you mentioned the 25 gigs. So 25 gig is definitely enough bandwidth to handle a single radio.
A single radio,
right, single radio. But the point is you can have like 6 to 9 radios at these cell sites, right? So you got to handle all of those. That's why I said even 100 gig is stretching it a little bit. And that's why we also look at either dark fiber or WDM. But the key thing is for every radio, we're going to have an eCPRI interface, and those data rates can vary depending on how much spectrum there is, a whole bunch of factors. Whether it's 4x4 MIMO or massive MIMO. There's a whole bunch of factors that affect that bandwidth.
Right.
But we got to get that back to this pool. Now, once we do that, okay, there's then we do this processing DU. Now, the CU is really sort of like we might say higher up in the layers, and so that there's not as much latency or requirement or bandwidth requirement in the mid-haul to go from the DU to the CU. So the CU could be sitting in the same DU pool here, or it could be sitting right at cell tower, but more typically it might be centralized in what we might call an edge or regional data center. Because in these far edge data centers, right, they're more limited on space and stuff like that. So you don't really want to put stuff out there that you don't necessarily need. One other point I'll make here, which is also a subject for another podcast, is as the service providers build out these far edge data centers, guess what? They can use them for MEC, which is mobile edge computing. Right. So there's all kinds of applications there, and that's a whole nother
there's a lot of use cases and opportunities there. Yeah, I agree.
Okay, so basically I've got the radios, I've got the DUs, and then I've got the CUs. So really what a lot of this comes down, there's the technical part, right? Getting better spectral efficiency. Mm-hmm. Also, the other part of the openness here that I should mention before we talk about economics, but the other part of the openness is in the old world, right, where I have a totally closed proprietary system, in terms of features and functions, you have a choice of what that vendor offers you and the time scale that vendor offers it. So, and that's it. You cannot change the features of that software. In an open environment, now we're in a situation where there's different software that could be combined. There's going to be a big ecosystem. There's going to be different vendors. Service providers might be doing their own thing. There's going to be open source here that's going to be evolving. Now, this is all new, right? So this is looking out in the future. But from an architectural point of view, that's the other key benefits. That's one of the things that when I talk to some of the service providers, they're very interested because they want to differentiate their service offerings, right, from their competitors. If they just have a vendor that's giving them, standard off-the-shelf stuff, there's no way, at least on the RAN level, to have any differentiation.
That's a good point.
Whereas this kind of architecture, now there can be a lot more innovation and differentiation.
Yeah, they've got some flexibility there to work with there and options. Yeah, that's a good point.
Yeah. So let's talk a little bit about economics. So first of all, before I get into the specifics of the economics of the RAN, one of the things that we've been doing at ACG over the last 3-4 years is we came to the conclusion that the way people are doing business case modeling is basically from the 20th century. It's not really the right approach for new networks. So basically, business case modeling has always been done purely with Excel, right? It's kind of a tabular format, and it's good at modeling fairly static situations. Now, as we move towards virtualization, towards cloud, there's all these components that are moving around. It's a lot more complicated. There's edge versus central data centers, there's transport. So what we've done over the last 4 years, we've invested in a platform that is a very flexible simulation platform of networks. So we can simulate a network, we can simulate demand, we can simulate services, we can simulate all kinds of software and applications, we can simulate data centers and servers and switches and routers and all these devices. But most importantly, in these simulations, we're simulating economics. We're focused on, it's a demand-based simulation, but we're simulating the cash flows and the economics. Well, OpEx, CapEx, and revenue, and very large numbers of CapEx. And then what we've done is we've created visualizations. You can see here on the right side of the diagram, these cash flows, and probably another podcast we'll get into more detail on what we've done there. But I want to specifically
that's a good point, because we do see there's a lot of tools out there that focus on modeling, but they're more associated with latency and performance. And as a former CTO myself, those are great, but then I used to have to go report to my boss and say, he would ask me a simple question: great, I see that you reduce the latencies to this amount, but what is the impact on cash flow? What is the impact on the overall TCO of the network? And those are answers that I just didn't have the capability at the point.
Yeah.
It looks like you solved that issue here.
Yes, yeah, and also the ability to simulate and model complex systems with a lot of flexibility, and that's essentially what we've been able to do. So now let's get back now to the Open RAN.
Sure.
Okay, so we talked about some of the key areas of savings. So the first one is spectral efficiency. Okay, so one of the things I talked about was that because we can when we centralize these DUs, and when we open up the software and we allow for innovation, what we've seen, and this isn't projected, this is seen and measured, okay, that we can increase the spectral efficiency, which basically means that you can reduce the expenses for radio, as well as just manage your spectrum better, which has a huge impact. So we can reduce radio expenses, which is very important. We can also reduce the BBU software expenses, because software is typically based on the number of carriers and the number of radios, and then also reduce the need for the DU servers and other infrastructure by doing that. So that's a key factor. The next one we talked about before also was open radios. So we use open radios. Guess what? They're less expensive. They're less expensive today. As we move forward, that's even going to they're even going to go down further in price, because as you get into these the open radio model, the manufacturers, the margin, they tend to be more commodity based. The margins are smaller, whereas in the current system, the margins are quite high on those, because there's no competition. Right. The next area of savings is what we call the DU pooling. So, it's kind of complicated putting these DUs out in these far edge data centers. It's a lot simpler to put them at cell site, okay? Right. But when we put them at the far edge data center, not only we get the benefits, associated with spectral efficiency and other things, but now we can also pool those servers and share them.
Right.
Yes, so we can share them. That creates much better efficiency, and we've seen some significant reductions in CapEx and OpEx. Yeah. And then finally, the BBU software. So when we go to the Open RAN solution, the BBU software tends to be less expensive than proprietary software. Why? Because again, it's open. Yeah. There's more competition. Eventually, we might even move to open source models.
Yeah, and I think you touched on an important point there. Like, even with the pooling, part of it is because initially some people look at the overall CapEx of, let's say, of the RAN network, and they're focusing on that. But there's a lot of efficiencies on the OpEx, kind of like if you look at infrastructure as a service, right, which what the cloud, you saw a lot of the efficiencies from a traditional IT infrastructure being embraced by some of these cloud operators. It's a similar concept that you're bringing cloud to this pooling capability within the RAN.
Yeah, that's a great analogy. So if we think of of the cloud of Amazon Web Services and Azure, right, and these things. Now today, everybody just takes that for granted. Right. It's like, oh yeah, of course. I'm going to do that, right? But before they came out with that was not something that
correct. Yeah.
You could do. You had to go buy servers and put them in the data center, and it was a big expense, right? So while this whole Open RAN thing is still pretty new and pretty complicated, it offers the similar kind of benefits, and that's why we're seeing so much interest in it. So Ray, let me I just want to go real quick to our BAE BAE tool. Right. Okay, so this is as I mentioned, we spent a number of years developing this platform, And there's actually a lot of very rich kind of output that we can get on this, and we'll probably do a whole nother session on that. But this is just to show some of the differences. So at the very top level, we can see the physical RAN and the virtual RAN and the differences between CapEx, OpEx, and TCO.
Right.
Now, one of the things, Ray, that as we were developing this, we do these comparisons, and the first thing that we'd be asked is why, okay, I see you have these differences in CapEx and OpEx. Why do you have the savings? What's driving the savings? Mm-hmm. And that used to be a very hard question to answer because it was all buried inside the models, and you had to go into detailed cash flow statements. So what we have now is a very simple user interface visualization of the expenses. So I can see here's my VRAN, my physical RAN, my OpEx and my CapEx for both. And here's the savings that I get. And then if I go down, I can see, okay, here's my CapEx and OpEx savings. And I can see on the OpEx side, here's the big things over here. And again, this is the virtual RAN. And this is the physical RAN. So you can see I've got power and BBU software and my cell site router. Over here, my BBU software is actually my highest in power, and you can see that it's higher. And in here, it shows you the big areas of savings. So
right. So that's an important. You bring up an important thing there, Peter, because when you look at some of those mobile modeling, especially even as you move to 5G, it sounds like an easy question, like you said, hey, what's driving the cost? But in some of the traditional models that we build, you can have 30, 20 tabs that address different functions to do the modeling. And there's a lot of cases where I would get asked that question, and I would have to fumble around, look at the computer to get to that. Now you're able to compare, I guess, right, any use case against any use case or any architecture against any, and be able to address and say what's driving the OpEx and what's driving the CapEx in a matter of seconds.
That's right. That's right. And then, by the way, this is an aggregate view over a 5-year period, but we can also look at it in any particular time period we want. Now, the CapEx savings, you can see that, here the key area of savings here is the radio unit.
Correct.
Okay. So this is where we're getting a lot of savings. We're also getting big savings on the BBU license, and then we're also getting some savings here on the basically we don't need to buy those physical units. However, there's an additional cost for the cell site routers, additional costs for the DUs. Mm-hmm. We also have the capability to say, I was just looking at the top 5 expenses. If we want to go down, we can see some of the other ones. But the nice thing about this view, Ray, is if you ask me that question now, I can answer that question just by showing you this chart. So
right.
Here's the key area. Here's the key areas where you're saving rank from top to bottom, right? And then the other thing we can do is we can look at it year by year and look at your TCO. So this would be your OpEx plus depreciation, or I can look at it OpEx CapEx, which is the CapEx. So CapEx is your actual cash flow, what you actually spend. The depreciation is where you take that CapEx and you depreciate it over 3 years or 4 years or 5 years, typically.
And this is a TCO, but you could do revenue models too, where you can look at margin as well.
Yeah, so with this one, we can do revenue, we can do all kinds of stuff. But for this particular case, we're looking at the TCO. Now, one thing I ought to mention, Ray, is that this is all going to vary, based on based on the use case, based on the service provider, based on the type of radios and environment. But one of the nice things is, since we have this very flexible modeling capability, right, we can go into these situations and relatively easily create a model of the network and then be able to see these results. And then if we want to go into more detail, we can go into the specific vRAN scenario itself, and in that scenario, we can look at we can get a bunch of other more detailed charts, right, where we look at year by year, and we look at the operating income, and we can look at, for instance, in the data center, we can look at cost per vCPU or the cost per memory, etc. And also we can get a very detailed cash flow statement, right? So with the cash flow statement, it has all the line items year by year, and we can export this to Excel. So anyway, so I guess I'd just like to leave you with the idea that the tool is very, very rich, and that's how we have come up with some of these things. So I think we've touched on a lot of stuff here, and I think there's a lot more to talk about. And I think the whole topic of backhaul and front haul, mid haul is a whole nother topic to itself. And then also there's a lot of topics just around 5G, around a lot of the other parts of 5G. So I think we'll leave that to another.
Well, hopefully you'll come more podcasts where we continue. But I think maybe to summarize is these mobile networks are large, right? And one of the questions I always used to ask when working in Wall Street was, so what? Why should I care and why now, right? And you address some of those points because for some deals, these could be tens, hundreds of millions of dollars. And having an understanding of this micro level visibility into the economics and what if modeling becomes important. And I could see why RAN being such a big part of the network and knowing what the cost of the network is important. So Peter, thanks again for joining this episode of the podcast. We're going to welcome you again, and thanks for the audience. Thanks, Peter. Stay safe.
Yeah, thanks, Ray. Stay safe, you as well.